These white containers are crossing a street in Tainan, Taiwan. They look ordinary until you read the name on the side, ASML. Inside is not a finished machine, but pieces of one. The full delivery can require 40 freight containers, 20 trucks, and 3 cargo aircraft. One machine arrives like an industrial migration. In another photograph, the convoy passes a neighborhood temple. It is the entire story in one frame. A machine designed in Europe, carried through an ordinary Taiwanese street on its way to a factory that supplies the world. And the technology inside those containers is still moving. On July 15, 2026, Intel and ASML announced that high-NA EUV was being used on selected layers of a high-volume Intel product. This is not a museum piece. It is the frontier advancing in real time, and only one company currently manufactures the commercial scanners that can take it there. But calling this a Dutch monopoly hides the stranger story. The machine is assembled in one country, depends on specialists in 3 others, and can still be stopped by a government signature. So who actually controls it? This is Chokepoint, the map of everything the world can't run without.
I'm your host. Welcome to Chokepoint. One episode, one thing the modern world can't run without. Who controls it, what it costs, what breaks without it. Before we go deeper, you need 3 words. 60 seconds. Let's go.
A chip is built on a silicon wafer through a long sequence of deposition, patterning, etching, cleaning, and measurement. Lithography is the patterning step. Light transfers a design into photoresist, so later processes know where material should stay and where it should go. An EUV scanner does not etch a chip. It does not package it. It does not make every layer. It performs one extraordinarily difficult job inside a much larger factory. And on the tightest layers of leading-edge chips, that job changes the economics of the entire process. The light begins with molten tin. Inside a near vacuum chamber, microscopic droplets cross the path of a carbon dioxide laser. The first pulse reshapes a droplet. The second turns it into plasma. That plasma, not the laser itself, emits extreme ultraviolet light at a wavelength of 13.5 nanometers. This happens up to 50,000 times every second. The source has to hit a moving target, create the same flash again and again, collect useful light, and keep debris from destroying the system around it. What looks like one burst is really a controlled industrial rhythm that must survive for production. Now, the light has another problem. Almost everything absorbs it. Air absorbs EUV. Ordinary glass absorbs EUV. So the optical path has to remain in vacuum and use mirrors instead of lenses. Those mirrors are not polished household glass. Zeiss describes multi-layer surfaces built from up to 100 individual layers, each only a few nanometers thick. Their job is to reflect enough of a wavelength that would rather disappear. Every reflection loses light, so shape, coating, vibration, and contamination all matter. The scanner is not one invention, it is thousands of tolerances agreeing at once. None of this appeared fully formed in the Netherlands. EUV was a decades-long research project involving U.S. national laboratories, chip makers, optic specialists, and equipment companies. In the late 1990s, a consortium backed work on an engineering test stand, not a production machine, but a place to prove that EUV masks, optics, sources, and stages could become one system. That distinction matters. A laboratory can create EUV light. A prototype can print a pattern. A production scanner has to do it across wafer after wafer, with repeatable alignment, usable throughput, and enough uptime for a factory that costs billions to keep running. ASML became the commercial integrator that carried this system into volume manufacturing. It later bought Cymer to pull the light source problem closer.
partnered with Zeiss on the optics, and kept pushing through years when the source was not powerful or reliable enough.
The monopoly was not one brilliant patent. It was the accumulated ability to make every subsystem arrive at production readiness together. ASML does not publish one universal list price, but its 2025 accounts give us a harder clue. It recognized 11.6 billion euros of EUV system revenue across 48 systems. Divide those figures mechanically, and the average is about 242 million euros per recognized system. That is not a sticker price. Product mix, upgrades, and revenue timing matter, but it tells you the scale before the fab, utilities, masks, process development, and service around it. The first key is Veldhoven in the Netherlands. ASML integrates the scanner, writes the system software, tests the machine, disassembles it for shipment, and supports it inside the customer's fab. In its 2025 filing, ASML called itself the world's only manufacturer of EUV lithography systems. That commercial position is real, but integration is not the same as owning every capability inside the box. ASML also warns investors that key components, especially in EUV, come from a limited number of suppliers and are often uneconomic to dual source. That is the hidden meaning of the containers. A finished scanner is the visible end of a much longer supplier network. The second key is Oberkochen, Germany, Zeiss Semiconductor Manufacturing Technology. Zeiss supplies the optical system. ASML does not own Zeiss. It holds a 24.9% indirect minority interest in Carl Zeiss SMT, while the Carl Zeiss Foundation remains the sole shareholder of the Zeiss Carent. So the only commercial EUV scanner depends on optics from a company its integrator does not control. The monopoly contains another choke point inside it. The third key is Ditzingen, also in Germany. Trumpf supplies the high-energy laser technology at the heart of the source. Trumpf is not an ASML subsidiary. It is an independent, family-owned company. Its newest EUV laser system is described as a 20-ton assembly containing roughly 450,000 parts. That does not make Trumpf a government veto. It makes it a capability dependency, a specialist industrial object that cannot be replaced by moving money from one spreadsheet to another. The fourth key is San Diego. Cymer spent decades developing lithography light sources. ASML bought the company in 2013 specifically to accelerate EUV. Today, Cymer is inside ASML, not an independent supplier, but the expertise, facilities, and source lineage remain American. Cymer's integration also corrects a tempting simplification. The US does not control EUV merely because one American supplier can vote on every sale. Cymer is owned by ASML. US leverage comes through origin rules, people, technology, and licensing jurisdiction, not through a fictional independent vendor veto. Put the four places together. Veldhoven integrates. Oberkochen makes the optics. Ditzingen supplies the laser technology. San Diego carries the light source lineage. The machine is Dutch at final assembly. The capability is multinational. Now add the legal gate. For a controlled export from the Netherlands, ASML applies to the Dutch government. The Dutch regime is an authorization system, with applications assessed case by case, not a universal global ban. But the Dutch decision sits inside overlapping rules. U.S. controls can reach U.S. origin technology, certain foreign-produced items, and some activity by U.S. persons. Japan operates its own equipment controls. These policies can align, but they are not one law and not one magical switch in Washington or The Hague. The immediate signature can be Dutch. The pressure around it is international. That is why the United States controls ASML is too simple, while this is purely a Dutch decision is incomplete. Control depends on the product, destination, components, people, and rule in force on that date. ASML says it has never shipped an EUV system to a customer in China. Then, from 2022 onward, the control perimeter widened. The United States imposed major restrictions on advanced computing and semiconductor manufacturing.
The Netherlands activated national controls for specified advanced immersion DUV and other equipment, then expanded them. US rules changed again. Japan implemented its own list.
In August 2025, the United States also ended a special authorization route used by some foreign-owned fabs in China. Its own release distinguished continued operation from expansion and upgrades.
That is the pattern to watch. Not only who can buy a new scanner, but who can expand, improve, and support an existing production line. The important point is not that one door closed once. It is that the boundary keeps moving with the technology, from the most advanced scanner toward other equipment, services, and expansion paths. This dependence runs both ways. In 2025, ASML's largest customer accounted for 23.9% of sales, and its two largest customers together accounted for 38%. The filing does not name them, so we will not guess on screen. ASML also ended that year with 38.8 billion euros of backlog. That is enormous leverage, but it is leverage over a very small club of customers powerful enough to finance whole manufacturing generations.
In 2012, 3 of those customers did something extraordinary. Intel, TSMC, and Samsung joined a co-investment program designed to accelerate EUV and the abandoned 450mm wafer transition.
Together, they took an economic stake of about 23% and committed 1.38 billion euros to research and development. But the shares were deliberately non-voting, except in defined exceptional cases. The customers financed the race. They did not acquire ordinary control of ASML. And that ownership is history. ASML's filings say the final participant canceled its remaining depositary receipts in 2023. Today's disclosed major holders are financial institutions, including BlackRock at 6.83% and Capital Research voting rights at 5.09%, not Intel, TSMC, or Samsung commanding the board. At this point, an honest viewer should object. If EUV is so decisive, how did Huawei ship an advanced phone chip without it? In 2023, Tech Insights identified SMIC's N+2 7nm class process inside Huawei's Mate 60 Pro. That result matters. It disproves the lazy claim that no EUV, no advanced chip. DUV multi-patterning can split a dense pattern across repeated exposures. The trade-off is more masks, more alignment, and more process complexity. Exact yield and pass count claims are not publicly confirmed by SMIC, so the safe conclusion is narrower. The workaround exists. It is not the same production system. EUV's advantage is often subtraction. On selected tight layers, one EUV exposure can replace a more complex DUV multi-patterning sequence. ASML's own model says EUV single patterning can mean about 20% fewer process steps per wafer than DUV multi-patterning, even though the EUV tool itself consumes more power. That is why the bottleneck is economic as much as technical. The question is not whether physics permits another route. It is whether that route can deliver the required density, yield, throughput, and cost at industrial scale. China is spending at a scale that respects the difficulty. Its 3 state-backed semiconductor big fund phases carried combined registered capital of roughly 95 to 100 billion US dollars at contemporaneous exchange rates. Registered capital is not the same as cash already spent, and it covers far more than lithography. Reuters later reported, citing unnamed sources, that a Chinese team had built an EUV prototype under test that generated EUV light but had not produced working chips. The organizations involved did not publicly confirm the technical details, so put the right words on screen. Reported, unconfirmed, prototype. A light source is not yet a production scanner, but the contest is live. The machine sale is only the beginning. In 2025, ASML reported 8.2 billion euros of installed base management sales, service and field options around tools already operating in fabs. That revenue is a clue to the operating model.
These systems are not delivered, switched on, and forgotten. Their productivity is managed across years through fieldwork and improvements. A service relationship can carry knowledge about calibration, replacement cycles, diagnostics, and performance that never appears in the purchase price headline. That does not prove a remote kill switch.
I found no primary evidence that ASML can press a button and brick a running scanner. The real dependency is less cinematic and more important: maintenance, calibrated replacement modules, software, upgrades, field expertise, and the ability to add new systems.
An installed fab may keep operating, but remove support long enough and uptime, productivity, and the path to the next generation become progressively harder to protect. So what breaks without this chain? Not every phone, not every car, not every fab overnight. What breaks first is the expansion path: new EUV capacity, replacement systems, advanced upgrades, and the process learning that follows them. Existing DUV fabs still matter. Mature node chips still matter, but at the frontier, delay compounds. A postponed tool delays qualification. Delayed qualification delays volume. Lost volume changes which products can be built economically and where. The choke point is not an apocalypse switch. It is a toll booth on the road to the next generation. And the toll booth is getting busier. In July 2026, ASML raised its full-year sales outlook to between 43 and 45 billion euros. It said AI-related investment was strengthening demand and planned to add 30% to low-NA EUV capacity of around 65 systems for 2027. At the same time, high-NA entered selected layers of high-volume Intel production. Scarcity is not frozen. It is being industrially managed while the next bottleneck is already arriving. High-NA also demonstrates why this story cannot end with one installed base.
The new platform changes the optics, the machine footprint, and the customer process around it. Each generation rebuilds part of the dependency. The frontier is not a warehouse of permanent machines. It is a moving agreement between research, suppliers, factories, and permission.
So stamp the map. Who controls it? ASML integrates the only commercial EUV scanner, but Zeiss Optics, Trumpf Laser Technology, Cymer's US source lineage, concentrated customers, and export authorities all hold part of the chain. What does it cost? Roughly 242 million euros per recognized 2025 system if you divide the accounts, not a list price. What breaks without it? The ability to extend leading-edge capacity on the same timetable and economics. What could replace it, and how long? DUV multi-patterning can substitute for selected layers at higher complexity. A new EUV production ecosystem would have to reproduce decades of source, optics, integration, service, and customer qualification. That is a multi-year industrial program, not a machine copied by decree. ASML sells the bottleneck. But the next question is stranger. If the scanner is only one line item, who pays for the factory built around it? And who gets paid when that factory is empty? That is the next node. Follow the map as it fills in.
Next, the machine gets built. But who actually pays for the $20 billion buildings these machines live in? That's node 2.